Hi, can you hear me?
Yes, sir.
Yeah,
Sir, would you? We do have time. Would you like to go through steps for sliding this slide so we could?
yeah,
Uh,
absolutely. I'll share my screen now.
okay. Yes, sir. It's visible and it's go through two slides, sir, so that we will see that transitions are smooth enough. Okay, sir. Good. Okay. Uh, Dear participants, thank you. I again thank you, humble for being on time. So we would start the session number 2 for this day. Uh, uh, Before starting, a few notice for all the participants. After this session, we would having a validatory function, and then after that, we will be giving you the test link. It would be a quiz, and the link would be open for only 2 hours. So in between the 2 hours, you need to log into it, attend the quiz, and then submit it back. So after 2 hours, the link wouldn't not be made open. So please be careful about that and go through that. You attend it on time. Okay, uh, with that putting aside, so it's my privilege to introduce you the speaker of this session. Dr. Devadas Bhatt P is an assistant lecturer in the Department of Metallurgical and Material Engineering in NITK Surathkal. He did his bachelor's in metallurgical and material engineering from NITK from the year 2013 and did his master's in IIT Madras in 2015. He received the prestigious DAAD IIT Master's Sandwich Scholarship to pursue his master thesis in KIT, Karlsruhe Institute of Technology, Germany. He completed his PhD in University of Lille via doctoral research grant from the French Ministry of Higher Education and Research in the year 2019 on the development of magnesium-based alloys for biomedical applications. Till date, he has published 14 scientific papers in reputed international journals, 6 book chapters, and presented in 5 international conferences. He is a life member of Indian Institute of Metals, Electron Microscope Society of India, Materials Research Society of India. Apart from magnesium-based materials, his interests include machine learning, energy-based materials such as perovskites, biofuel cells, and dental materials. Sir, we are privileged to have you on this session, sir. Over to you.
Yeah. Thank you, one and all. First of all, I would like to thank the Institute JNNC Shumoga for giving me an opportunity to present a lecture. Also, thanks to AICT Training and Learning Academy for having such a wonderful session. So I think we have had about 14 sessions so far, and uh, I hope, including mine, 14. So I hope everything was so interesting. I really hope that mine isn't too repetitive, but then, well, it doesn't matter also because even if it's repetitive, we can relearn the concepts and understand them very clearly. I would like to highlight before starting my presentation is that we had a couple of lectures, starting from the keynote lecture from Professor Manoj Gupta. And the work, whatever I've done, I have also done, I'm also presenting some of my work, which I have done at NUS Singapore in Prof. Gupta's laboratory. Okay, so we'll start our presentation. So my name is Devdas Bhatt. I'm an assistant lecturer in the Department of Metallurgical and Materials Engineering. And this is my contact. If anyone of you are interested in contacting me after the lecture, then please do not hesitate. Yeah. So let me go through the overview of my presentation. So in the beginning, I will be introducing my subject. Then I'm going to talk about the magnesium degradation. Then I'm going to talk about alloy development. One of the important characteristics of material science tetrahedron is the determination of structure, right? So that's the first thing that we do when we synthesize a material. So we are going to talk about the microstructure. We are going to relate it to the mechanical properties, and then we'll have a small discussion, followed by biocorrosion. So engineering, that is the general corrosion, and then you have what is called as biocorrosion. The equipment could be the same, but then we use different solutions, different medium, different conditions. Then I'm going to talk about fluoride coatings, and then some points on the biocompatibility studies. Okay, so I'm going to emphasize much on the introduction aspect. I'm very sure that you've already had some introduction in the earlier sessions, but then let me re-emphasize that and probably bring in new concepts. Okay, so when it comes to the world of biomaterials, right? So what exactly is a biomaterial? Something that is compatible with the biological functions of human body, right? So you see here, one of the first metallic biomaterial, okay? So nowadays we talk about implants, stents and all that. So these are something that we could introduce inside the human body. But then there used to be a time here that there is some kind of a plate here, a metal plate. So we call this particular terminology that is the bone fracture fixation. So you're fixing it from the outside. Okay, so there is some kind of a fracture here. Okay, and then you introduce a plate from the outside, and then you introduce some kind of fixation method, some kind of screws in order to fix the plate so that it adheres properly onto the fracture. Okay, you see a photograph here of a famous doctor, surgeon by the name Karl Hans. So talking about somewhere in the period of 1886. Okay, so the reference here is Journal of Cranio-Maxillofacial Surgery, right? So maxillo is this part of our body, right? So you can go for this particular journal if you want to read more about the new developments happening in the cranio-maxillofacial region, right? So metallic plates were introduced by Professor Lane more than 100 years ago. And you have here Karl Hansmann. He was one of the first person to develop and present a procedure for what you see here, cutaneous fixation of bone fragments. So they used what is called as a plate and a screw system. Okay, so we regard Karl Hansmann as the inventor of plate osteosynthesis. Okay, so the plate and the screws, they are stuck out of the wound and they were removed after about 4 to 8 weeks. Okay, and Professor Lane, he was also knighted, so we call him Sir Lane, and he was reporting the corrosion of this material during the healing process 2 years later. Now, some other examples that you can see here. Okay, that is the fixation from the outside. Okay, so with every development of material, you will see that people face certain problems, people work on it, people develop new strategies. Something like our real world, what we can talk about the global pandemic, right? So we identified the problem, and now we are working towards how to tackle that problem, right? So we are working towards that in such a way that tomorrow, if such problem arises, how to be alert. So similarly here, whenever you develop a new material, you understand what problems you face and accordingly you tackle them. So the problems which they faced was insufficient strength and corrosion. Okay, so these are the two main problems faced by the metallic biomaterials. So in the year 1920s, we had the advent of corrosion resistant. Some material that you can think of is stainless steel. One grade of stainless steel is what we call as 18-8 stainless steel. 18 refers to 18% chromium, percent percent. So introduction of such 18-8 stainless steel was proven to be solving this particular corrosion problem. So introduction of that material, it fostered the development and clinical use of metallic implants. All right. So what you see here is this particular photo. This is drawn by, again, a doctor called as Luhr, L-U-H-R. So this is one of the first types of compression plates. Okay, so normally providing some sort of a compression load. Okay, the photograph, what you can see here, yeah, now that is the trajectory system. Okay, so some kind of stress analysis which you can maybe mental method. So this is the trajectory system of the mandible. So this is the mandible, right? One of the largest bones of the skull portion, right? All right. So one of the first person is Luhr, L-U-H-R. So he developed the principle of the compression plate osteosynthesis. That is what you see here in the figure, what I'm showing here. Well, so you see here, you have some sort of screw mechanism here. All right. And you know that you have this recesses, right, for the screws. Now, you see here, the recesses are prepared in such a way that it should be prepared at the far end of the plate hole. So you have a plate hole here, and it is placed at the far end of the plate hole. And later, when you tighten the screw, the fracture end, they are approximated by the effect of the spherically shaped holes. So earlier, the plates, this kind of plates were made up of stainless steels. Then you have Italium alloy. You have pure titanium. Yeah, all these materials were used earlier. Again, here you have certain more developments in that particular area. So then what they did was they did some sort of a tension banding. Okay, then you know that we can also introduce what is called as wire ligatures. Yeah, some sort of a wire, metallic wires over this particular region. And then here you can see some new technology. Now that is the reconstruction plate. It is made up of titanium. Now you have a screw here. You see the head of the screw. Yeah. Now, to this particular head of the screw, introduce an so that you lock the hole. Yeah. So you lock the hole of the plate. So such kind of mechanism is called as THOEP. Now it stands for titanium coated hollow and reconstruction plate system. So you see the head of the actual screw here, it is hollow and it has got certain threads inside which a smaller screw was inserted. So this, it spreads the outer walls of the first screw and it presses against the plate. Now what does it do? This particular mechanism, this leads to some sort of a stability which is independent of the contact between the plate and the bone. Okay, so this is all different advancements what we see in metallic biomaterials. Yeah, here you see this is some sort of a regular mini plate, and you see here some sort of a self-tapping screw. Here you have a mini locking system plate, and here again you see the different design for the locking screw. Right? Now, let's slowly come to our topic. It is very important for us to understand the history, right? So whenever I talk about some current trends or current features, we should learn history and we should respect history as well, right? Because history teaches us a lot of things. To start a research, what you have to do first is literature survey, right? So we look at what people have done before. We learn from what they have done and we try to adapt or understand and modify accordingly and try to develop that particular technology or a material. Here you see a few examples. Now, before that, we know we have certain organizations, right? You have ASTM, that is American Society for Testing of Materials. You have FDA. Then you have several other standards. There is international standards, ISO you have. So we need to know what are these standards, and we have to design our experiments accordingly, right? So as metallurgists or mechanical engineers, you know that if you want to carry out a tensile test, right? So to design the specimen, we go to the ASTM standard, we design the specimen accordingly. If you want to carry out etching method to determine the microstructure, we again go to ASTM standard, and then we see, okay, for magnesium, I should use this etchant. For stainless steel, I should use that etchant, etc. Similarly, when we talk about such standardization techniques, ASTM, it has formed some sort of a committee on such medical and surgical materials to standardize the metals for medical applications. So today, under this particular domain, we can see more than hundreds of different types of alloys, composites, hybrid materials, which can be used as implants, okay? And common general categorization we can do, that is, you have stainless steel alloys, cobalt chromium alloys, titanium and its alloys, and you have noble metals, for example, right? So in this particular figure, you see certain examples of medical implants wherein metal can be used. Okay, so what makes metallic biomaterials so important? So there are notably two key features. First of all, that is the structural function, and the second one is the inertness of the material. Okay, today it is desirable that an implant also possesses several other functions such as bioactivities, biofunctionalities like blood compatibility, bone conductivity, and so on. Okay, so what do if you want to enhance bone conductivity? If your metallic material doesn't suitably provide such bone conductivity, I design a coating, right? So I do certain surface modification. Okay, you could probably coat the material using HAP, that is a hydroxyapatite, okay, calcium phosphate pentahydrate, or to enhance blood compatibility, that is, the implant should be compatible with the bone, right? So if you introduce an implant inside the human body, our human body should accept it as its own. Any foreign, a human body will not accept just like that, right? So first it will inspect properly, and then, okay, slowly it will start to welcome inside the human body, right? So that is called as compatibility. Okay, something that we humans also do in general when we try to look for new friends, right? All right, so here you have a very small table. I hope it's visible. And these are certain body conditions, yeah, which our metallic implants will be subjected to. So like I said before, they will be in contact with the living tissues, maybe forever, maybe for some stipulated amount of time, right? So until that particular period of time, they need to be biocompatible. Okay, so you know our body temperature is about 37 degrees Celsius. pH, it varies, right? So in the blood, I can say that On an average, it's 7.35, 7.4. Some of them consider like that. In the cells, it will be different. Stomach region is acidic, and so on. Desired oxygen values are also different. In the arterial blood, it will be different. In the venous blood, it will be different. You know why, right? And the presence of chloride also is different in the serum, in the interstitial fluid. You know that different bones have different strength, right? So some of your bones are stronger, some of them are not so strong, and you've got certain parameters over here, right? So what is an important parameter for metallic device is adequate mechanical properties such as strength, stiffness, fatigue, and most importantly, appropriate density. Okay, please remember this, appropriate density. Okay, we'll come to that density part slightly later. Now, another important parameter our metallic implants should not be is that it should not be magnetic, right? So why? Because if you have a metallic implant that is magnetic, and if it has very high if it has very low density, then well, you know that it has to be compatible with the MRI techniques, right? So if your metallic implant is magnetic, then it could interfere with the MRI techniques. And it should be enough dense. If it is not very dense, then it will not be visible under X-ray imaging. Okay, so X-ray imaging, how it works with the density, right? So your implant should be enough dense so that it is visible under X-ray imaging, right? Now, what kind of loads our implants will be subjected to? You have static loads, dynamic loads, several other types of loads, right? And for that, it requires a very good combination of strength and ductility, right? So that's the reason why metallic biomaterials are preferred over other classes of materials like ceramics and polymers. Okay, ceramics are also used in different applications. Polymers are also used in different applications, but something that requires adequate strength, we always go for metallic biomaterials. Now, these are the different types of metals that are used in biomaterials. Now, how did I classify that? I classified that depending upon specific implant application. Now, what is the one common material that you can see in the image here, that is SS316L, right? So it is the most used alloys in all implant division, ranging from orthopedic to dentistry, all the way till dentistry, right? Now, if you want an implant to have a very good wear resistance, cobalt chromium alloys, because they impart very good wear resistance. Okay, now again going back into the root of the basic material science tetrahedron, right? So you have structure, property, processing, performance. Now you can also introduce another component there, that is ICME, right? So integrated computational materials engineering. So people are nowadays, doing a lot of research in the area of computational material science, and I highly encourage everyone to also look into that perspective, so that we should not merely focused on one particular domain. See what this pandemic has done to us. The past 18 months, we are not able to perform many experiments. So computational materials is also gaining importance these days, right? So what is the basic characteristic of metals? It's the chemical composition, right? So chemical composition is the important aspect which determines the microstructure and the amount of phases. So then it will determine their properties. Okay, for example, mechanical properties, right? So giving an example, I can tell you, let us say we take pure titanium, for example, right? So a particular famous alloy of titanium. The first alloy that comes to your mind could be Ti64. In short, it is titanium, 6 aluminum, 4 vanadium, right? So why do we add 6 aluminum and 4 vanadium? That is to increase its tensile strength, right? Now, besides composition, we talked about processing, right? So what does it mean? It means the metallurgical state of the metal or an alloy. It will change the mechanical properties. An example, that annealed condition, it will have better ductility than that of cold worked. Also, then comes the method by which you synthesize the material, right? The process of synthesis also will affect the microstructure and properties. Again, a small example, cast metallic implants usually possess lower strength than the ones which are prepared by 4. Okay. All right. So you have here certain examples. That is the austenitic stainless steel, 316, 316L. Right. So first, SS used to contain 18 chromium and 8 nickel. Now it makes it more resistant to corrosion, and it is lower than steel. Now, apart from adding chromium and nickel, can I add molybdenum, for example? Okay, so if you add molybdenum, what will happen? It will further increase the corrosion resistance. That is nothing but the type 316. Now, if I reduce the carbon content from, for example, about 0.08% to 0.03 weight%, if I reduce the carbon content to that extent, you can increase the corrosion resistance against the chlorine solution, which is nothing but your 316N. Right? Now, let me first go through different materials. So, like I said before, cobalt chromium alloys are known for the excellent wear resistance, where they have been used in dental industry for more than several decades, and also in artificial joints, right? So you have an example here, the cobalt chromium moly, or cobalt chromium nickel moly, or cobalt chromium nickel moly iron alloy. Yeah, so these alloys, they are wrought alloys, and they have been used in making loaded joints, such as for the hip and for the knee. Precious metals, right? Gold, silver, and platinum. They're used in dentistry. Why? Because they have good castability. You know that such gold and silver, they have very good castability, right? They have good ductility, and they also are excellent corrosion resistant materials, right? So that's why we go for dental amalgams made up of silver, alloy, of course, and gold, right? Now, if I add in the dental alloys, you have other types of alloys. If I add copper, I can add copper to the silver gold silver system. I can also add palladium to the silver platinum system. I can add zinc and lead. Okay, so lead, you call that a solder material, right? So if I introduce lead into this system, I call that as dental solder, right? So it's basically used for joining or for the teeth problems. But then there are certain drawbacks of certain such materials, right? So nickel, it's very toxic, right? Nickel is carcinogenic. Cobalt is acutely toxic at larger doses. Again, here you have the nickel toxicity. Mercury is highly toxic, right? Amalgam means you will have mercury, right? And again, shape memory alloy, you know that nickel titanium is an example of a shape memory alloy. And again, you have nickel there, nickel toxicity. You have problems with the conventional metallic bioimplants. Well, again, we are slowly coming into our topic. So one can classify implants again into two different types. One is the permanent implants, and then the second one is the temporary implants. Certain implants have to be permanent. Well, they cannot be temporary. Whereas certain implants can be temporary. So still people are going for permanent implants, even for places wherein a temporary implant could do its job. Now, what are the certain problems associated with the permanent implants? The first one is the risk of post-operative infection. Okay. Number two is increased incidence of pediatric trauma requiring surgical intervention. So suppose, for example, like I said before, you have a case, medical case wherein a temporary implant could do a job, right? So a bone, new bone will be growing, and the permanent implant will cause obstruction to this new bone that is growing. And after the permanent implant has performed its job, you have to remove it. So you have to perform second operation. The first operation is to introduce the implant. Second operation is to remove the implant. So it adds to money, it adds to pain borne by the patients, especially trauma is a medical terminology which is unbearable pain or severe pain. Pediatric means, of course, it's associated with children, right? Third and most important criteria we are looking for is what is called as high stiffness of the standard fixation hardware. So you know that the titanium, right, which is predominantly used as implant materials, they have higher values of Young's modulus, right? So I've given you an example here. Okay, you see here that you have a bone here and you have your implant here. Okay, now for the same amount of strain, for the same amount of strain introduced to the bone and metal, if your metal has higher elastic modulus than that of the bone, you see here in the stress strain curve, I have the elastic modulus for bone here, the elastic modulus of bone, the slope of this curve is here. So the metal will have greater elastic modulus compared to that of bone. So for the same amount of strain, the metal here will be taking greater amount of stress. The metal will be taking greater amount of stress as compared to that of the bone. Okay? So that is what we call as stress shielding. The bone will be stress shielded. Okay? Greater amount of stress is taken by the metal. Therefore, the bone will be stress shielded, and a patient will be facing a lot of problems if there is no uniformity in the stress distribution between the implant and the bone. Okay? So that's the reason why there is a need for temporary medical implants. There are certain other problems which are associated with conventional metallic bioimplants. The first one is the release of toxic metallic ions or particles by corrosion or wear process. Okay, so these permanent implants are designed such that they're permanent. There should not be any sort of metallosis or the removal of metallic particles from the implant, right? So they are designed such that there is no removal of such particles. Now, because of the interaction with the human body environment, because of the loading mechanism of our body, yeah. So what happens is these implants will start to get weared off, and slowly there will be some amount of debris that can be collected. It could be very minute, but it could be toxic as well, right? And the second one, I said the possible secondary surgery to remove the material. Well, I'll come to this table little later. Okay, now this is the transition slide from the permanent implants to the temporary implants. Why magnesium and why we should go for implants which are biodegradable and biocompatible. Okay, so earlier we had a paradigm, right? So far, whatever I've said, okay, you should have very good strength, your implant should be corrosion resistant, and so on, right? Now we are slowly shifting this paradigm here, right? So we have this new degradable biomaterials, which constitute a novel class of bioactive biomaterials. Now they are expected to support healing process of the diseased tissue or organ and slowly degrading thereafter. Okay, so in the present days, as all of you would know, the study of innovative biodegradable materials, it is one of the most interesting research at the forefront of biomaterials. Why? Because as you all know, like I said before, when it comes to material development, we all expect a very easygoing life or happy life, for example. So our society expectations increases as time goes on, right? So we would like to have technology developed in front of us, whether it is in the field of engineering or medicine, right? So the increased society expectation for a better quality of life, it has fostered many biomaterialists to develop new technologies to provide implants with high clinical performance. So far was what we saw, the paradigm of implants must be inert and corrosion resistant. Now let's break that paradigm, or let us shift from that paradigm. Now this paradigm, it is challenged by the advent of this new class of degradable biomaterials. Okay, so I come back to this particular slide. As you can see here, certain important parameters. You have what is called as a density, then there's a compressive strength, tensile strength, Young's modulus, and elongation at fracture. We are more interested in these two aspects, that is a density and Young's modulus. So one of the important characteristics of the biodegradable implant is that the value of density and Young's modulus should be close to that of the human bone. Okay, so you see here for the cortical bone, the density is about 1.7 to 2, and magnesium, the density is 1.74, right? So for other class of materials, you see that it is 2 times or 3 times higher. Similarly, we have the values for the Young's modulus. Okay, Young's modulus concept I've already explained to you. If you have a higher Young's modulus, then you will have this effect of stress shielding. That is, the bone will be stress shielded as compared to that of an implant. All right. So we have already broke the established paradigm that the metallic biomaterials must be corrosion resistant. Okay, and I'm giving you one classical example here, wherein this is a clinical problem. It needs only temporary support or healing. Okay, so this particular temporary support can be provided by an implant, which is made of degradable biomaterial, which will allow the implant to progressively degrade after fulfilling its function. Okay, so how this concept was evolved. Okay, we all know examples of certain polymers which are used as sutures, right? So these sutures are also nowadays biodegradable, which means after the wound healing takes place, you will no longer see the suture. The suture will be degraded within. Okay, so this concept of biodegradation was taken from such a particular concept from the polymers. Okay, now the implants that degrade, especially those which are made up of metals, we are in the domain of metals today. It is considered as a novel concept which breaks this paradigm again. Okay, now the concept is very simple here. You require the presence of certain implants temporarily. It will support the healing process of a diseased tissue. So you see here an example of a stent. Yeah, it's a temporary implant. So first you introduce the stent using some sort of a catheter, right? And then there will be plaque region here. So plaque region is something that narrows your, in our case, what we have taken a coronary artery, right? So the plaque region is something that we need to work upon. So for the easy flow of blood through the artery, what we do, we introduce a stent, right? So how do we introduce a stent? We introduce it via a catheter. Then there will be a balloon. So that balloon will be inflated here so that your stent material gets expanded. And once the stent material is expanded, your balloon, you are going to deflate and you are going to remove it. And then the expanded stent will retain its structure and it will allow the blood for the easy flow inside the artery. And the plaque, well, how to tackle this plaque? Our own body will do it after a certain period of time, or we should go for good lifestyle or good food habits, etc. Right? So this is one example wherein once the plaque gets healed, you no longer require that stent, right? So that stent, nowadays, one could remove it, for which again you should go for a second operation. Now, if that particular stent is biodegradable within a period of 3 months or 6 months, it will gradually degrade. So implants will play a role until sufficient bone joint is formed and then degrade and are replaced by new bone tissue. So there are different classes of alloys. You have magnesium based, you have iron based, you have zinc based, which are coming under this classification of biodegradable metals, right? So iron is essential to metabolism. Anything which is in excess or anything which is deficient, it can be toxic. Iron, in comparison to magnesium, it degrades slowly. Whereas stents here, it requires slightly faster degradation. So we don't go for iron, we go for magnesium. Now, how to design an ideal implant? First and foremost, what we should do is the selection of material. Then we go for the mechanical properties. All right. So you see here the graph which is plotted as a function of time. So the implant material, the mechanical properties of the implant material should degrade as a function of time so that the bone will increase in its mechanical properties over a period of time. So when the bone grows, the implant should degrade proportionately. That's mechanical properties, and third is the manufacturing, right? So if you want to design that is having controlled biodegradability, I should have a material which is biocompatible. My synthesis methodology should be economical because that's how engineering works, right? You should not process or develop a material which is expensive. Why? Because it will not go into the hands of common people, right? You can hear me, right? Hello? Someone said mute.
No, sir, it's audible.
Okay.
Go ahead, sir.
Yeah. Then comes the purity, right? So engineering materials for engineering applications, of course, we are concerned with the purity, but then sometimes if you perform, let us say, an EDS analysis or some sort of spectrometric analysis, you will see that you will have very small fraction of impure elements, which could come from the raw material or which could come from the processing methodology that you have used. So you will have certain tolerance for that when it comes to materials for engineering applications. But for such biomedical applications, you should ensure that your material is absolutely pure and it should not induce any toxicity to the human body. Well, mechanical properties, the implant should have mechanical properties similar to that of human bone. These are the different mechanical properties. Also, manufacturing, we all know that these particular parameters, it should be effective fabrication, the raw material quality should be exceptionally high, you should have a very good surface finish, and less lead time, of course. Okay, because once you prepare a particular material, you know that it is not ready, right? It has to get a lot of approvals. There will be an FDA approval, there will be European Union, EU mark, right? So once you get these approvals, which take a lot of time, and only then it will go into the trial phase, wherein first it could be introduced inside rabbits, or it could be introduced inside mice, and then it goes to the human body, right? So we should ensure less lead time, less time required for the manufacturing. Now, what is the answer to all these parameters? All these parameters can be easily attained by the class of materials, that is the magnesium-based alloys and composites. Okay. Now, again, like I said before, history is very important. We go into the history and then we learn from them, and then we apply that into our research. So again, a very brief history into what people have done before. So back in the 1878, we have Hughes. He was the one who first reported the use of magnesium. That's for the vascular closure. And then for the treatment of joint disease, Payer, he has introduced the concept of magnesium plates. And then it is followed by Slumsky. That is the human implantation of magnesium into temporary stabilized joints. Then you have the Dr. Lambert. So Lambert is very renowned personalities in this field of biodegradable magnesium implants. And I suggest you please go through this link for any extra reading. Okay, so Lambert was one of the first to, well, he's called as the father of temporary orthopedic implants, right? So in the period of 1930s, he was the one who did a lot of research in animals and humans, right? All right, so with all this, development in the history, you could see some certain chronology, but you can see a small gap here, right? There's a gap of about 40 years from 1940 to about 1980. Many reasons behind this gap. This gap is found in almost all research. That is, of course, the Second World War is one thing. And also, you could see that in this particular period, people faced a lot of problems with respect to the implant based on magnesium. That is, people faced problems of rapid degradation and the evolution of hydrogen. These are the two main problems which frustrated the surgeons, right? And then they abandoned the biomedical applications of magnesium, right? So in these 40 years, nothing happened. But later on, slowly you can see that they started doing research on wires, and then they went for plates and screws and so on. Okay. Here is a small representation of the examples of magnesium-based implants. You can use them as bone implants. You can use them as a wound closing device, right? So, for example, you know that inside the stomach you can introduce an endoscope, and then once that wound, if it has to be closed, then you can use an implant made up of magnesium. Okay, stents I've already explained. Scaffold also is another area wherein you can explore. Now here you see slightly old data, but what I wanted to show you is the trend here, right? This is nothing but the number of publications on the subject of biological applications of magnesium alloys and its composites. Okay, I'm very sure that you may have higher numbers than that, but It's just the trend that we see here is that the trend is increasing, right? The research on magnesium alloys and composites is increasing with every year. Now, certain problems again, which we are not able to understand, or which we need to tackle them. First and foremost, expensive. Why? Because it's a new material. People are busy patenting the material, and before it comes to the common man, it has to go through a lot of approvals, which requires time, which is expensive, right? Number two, degradation mechanisms not well understood. Okay, so when it comes to degradation, if we are talking about degradation inside a human body, it takes a certain period of time. Okay, and then there may not be any short-term effects, but there could be certain long-term effects, okay, which needs to be properly studied. So the uncontrolled degradability. Okay, like I said, the implant degrades over a period of time. The implant will have a proper geometry in the beginning. Now, once some corrosion takes place, say for example in the exterior, the implant will no longer have that same geometry, right? So the geometry will be changed. Once the geometry changes, you know that the stress distribution will change. And because of that, the corrosion and the mechanisms also would change over a period of time. Okay, so this degradability is not really uniform. Okay, so you will have degradability in the initial phase, degradability in the middle phase, degradability in the end phase. Okay, so you will have uncontrolled degradability. This is something which we need to. Now, we talked about ideal implant. Now we will look into what are the different parameters that influence degradation. We'll start from here. Processing. When it comes to microstructure, you can tailor the grain size. You can reduce impurities. You can play with the secondary phases. Okay, you can make them fine, you can make them coarse, you can make them uniformly distributed. You can do certain heat treatment. You can change the surface, you can modify. Now, when it comes to the testing method and testing conditions, you prepare a sample, right? So these are certain in vitro tests. In vitro means what you perform in the lab, right? So the position of the sample inside the electrolyte is also very important. How frequently you are going to change the electrolyte when you are going to perform the corrosion studies. The size of the sample, and then very important, what we have here is the SV ratio, or the volume to sample surface ratio, right? This is also very important. So all these parameters you will see in the HTM standard. We follow that and then we perform the test. Then comes the surface preparation. Whether you're going to perform the test in a dynamic fluid, whether your fluid is static, what is the atmosphere that you have in the testing condition. So if we want to mimic the body conditions, we go for 37 degrees Celsius body temperature and 5% carbon dioxide atmosphere, right? And then the electrolyte. The electrolyte that you choose, how is it close to the body plasma or the blood plasma, you know? The pH value and the concentration, all these. Testing method as well, you have different testing methods. I'm sure you all know what are the different corrosion tests that we have. Now, these are certain corrosion reactions. You have the magnesium, which becomes a hydroxide. And the overall reaction, you see the evolution of hydrogen, right? So depending upon how much hydrogen is evolved, you can also perform a corrosion test based on that, right? So primarily magnesium undergoes pitting and galvanic type of corrosion. So what is pitting? Pitting is nothing but the localized form of corrosion, okay, where you have certain cavities or holes that are produced in the material. Okay, and I'm very sure that in the earlier sessions we had a corrosion expert, Dr. Shashibhushan Arya from our own institute. I'm very sure that he has given you a very brief, complete understanding of the corrosion mechanisms. Okay, but why pitting is dangerous? Because it is very difficult to predict and it is very difficult to detect. It is also very difficult to design against such a mechanism. Why? Because the corrosion products which are formed, it covers these pits. You cannot see the pits. The products that form, it covers the pits. You already have a pit inside, right? So, yeah, it's very tricky condition also. So, a lot of disasters have taken place in the world because of pitting corrosion. One particular example I can give you is there was a gas pipe, okay, in Mexico, wherein a pitting corrosion took place, and like I said, it was not able to. People were not able to detect that, and because of such corrosion, such a pitting corrosion, gas pipe leakage took place in Mexico, and it resulted in death of about 200 people, right? So it is very important when you design a material is to look into what are the different parameters that are involved in the degradation of magnesium alloys. All right. So now we will go for the processing. So I'm going to show you some snippets of how we have synthesized our materials. So we have used what is called as a disintegrated melt deposition method, in short DMD. All right, so we have a setup over here, and this is a 3-chamber setup that we have used, and this is a schematic that you see here, right? So we have a crucible inside, and then we have a nozzle here, and here we have a mold, and we have the argon gas supply inside the crucible, and also perpendicular to the flow of the material, right? This is the crucible that we have used. This is the mold that we have used, the stainless steel mold. Crucible is made up of graphite. All right. So this is the thermocouple, this is the motor, and this is the argon inlet. So the mechanism behind this is once the melt, it attains a particular temperature. So melting point of magnesium is around 660. We heat it 100 degrees Celsius above the melting point. We heat it up to 750. We also add other alloying elements that we require, and lower melting point. Barium, calcium. Calcium has melting point of about 840, I think. So once it attains, once everything gets melted, it will take about 2 hours or so. We then use a motor and stir it so that they get uniformly distributed. And then we then start the argon flow here, right? And when the pouring takes place, the droplets get atomized, and then it will get deposited onto the mold. Okay. So this is how we get a billet from the DMD method. And after turning operations in lathe, you will get something like this. And once we take it to an extrusion machine, this is how you get an extruded rod. All right. So one of the advantages of this particular technique is we have increased yield for this setup with the least metal wastage. So following which we go for extrusion. So this is the extrusion setup that we have used, and this is snippets of how the extruded rod looks like, right? These are few density values. You can see for the as extruded, the values of densities are higher as compared to the as DMD materials. Now, what are the different alloying elements that we have used? right? What are the different secondary phases that have been formed, and what is their distribution? So why alloying is to improve the mechanical properties, also to improve the corrosion resistance, also to improve the biocompatibility, and most importantly, what we require is controlled biodegradation. Of course, with every research, we follow challenges. What is the challenge for us? That is the level of toxicity controlled, and we still do not know the long-term effects of certain elements, right? So this particular challenge is multidisciplinary. Okay, why? Because who does the alloying? The metallurgists do the alloying. Who does the check on the toxicity levels? The biomedical engineering people, they do that toxicity level check. So this is the uh, multidisciplinary challenge faced by the domain of metallurgy and the domain of biomedical engineering. So our alloy design should be confined to a range of alloying elements that are biologically non-toxic while still providing the requisite mechanical properties. So like I said before, alloying element like zinc, for example, right? So the solid solution limit is about 6%, 6 to 7 weight% of zinc in the magnesium zinc diagram. Now, I add 1 zinc, I add 2 zinc, 3 zinc, 4 zinc, 5, I go up to 6 weight% zinc. Now, if I go with that, I'm going to increase the mechanical properties, right? So 6 zinc is always good, but adding so much of zinc, can it be toxic? Will it be toxic to my implant? That aspect also needs to be checked. Okay, so it is not just increasing the mechanical properties as you wish, which is what we mostly do in the engineering applications. You should also look into whether your alloying addition, because too much is too bad, right? So whether your alloying addition is toxic, right? Now, we take a few attributes. So we have magnesium. Why magnesium? Its property is similar to that of human bone, but magnesium is subjected to rapid corrosion. So then we add zinc, right? So zinc will enhance ductility and deformability. It will increase the tensile strength. Now, what is RDA? RDA is the recommended dietary allowance. Okay, you will see in many food items that you purchase or calcium tablets maybe, you will have the doctor's advice, right? The RDA is fixed for every element. So RDA for zinc is about 15 milligrams per day. We get the zinc by eating vegetables, etc. So what does zinc do? Zinc will elevate the corrosion potential of magnesium. Calcium is an excellent grain refiner. Why calcium we are adding? Because it is also a major component of human bone. And the RDA for calcium is quite high, right? So about 1,000 milligrams per day. All right. Now, coming to rare earth. Okay, the topic of our presentation is novel magnesium rare earth based alloys and composites, right? So, Professor Uday, but he's also already explained what is rare earth, right? So you have certain class of elements, for example, you have yttrium, and then you have all the lanthanide series, you have the actinide series as well. Okay, so we'll classify what are the different rare earth elements. So rare earth alloying, it will alter the number density and the size range distribution of the native intermetallic phases. Okay, it could be the beta phase in the AZ class of alloys. So it will modify the distribution with respect to the number density of such phases. It will also lead to what is called as scavenger effect. Okay, so what is this scavenger effect? This rare earth, when you introduce it into your alloying, it will interact with the impurity elements in the alloy. Okay, and whatever adverse effects those impurity elements would provide to your material, the rare earth will make sure that the interaction between this rare earth with the impurity elements will not have any direct influence on the bulk corrosion. Again, why rare earth? Because it will lead to improved stability, the surface oxide stability of the alloy. We are going to classify the rare earth elements into two groups. So one is the low solubility groups, which is neodymium and cerium. Then we have the high solubility, that's yttrium, gadolinium, dysprosium, erbium, and so on. Okay, so in our case, we have taken erbium here. All right, so we have developed ternary systems, MgZnRe, by playing with the composition. We also designed that is magnesium, calcium, erbium. Okay, so the microstructure consists of number of different phases, such as icosahedral phase, W phase, Z phase, Laves phase, depending upon the ratio of zinc and rare earth content. So different number of phases, hence you will have different mechanical behavior. Now these are the compositions that we have designed. We have taken pure magnesium, which is a standard. We have added zinc to study the effect of zinc, calcium to study the effect of calcium on zinc. Then we have added erbium to study the effect of erbium. Then we have designed two alloys such that their zinc to rare earth ratio, here it is 1. Here the zinc to rare earth ratio, here it is 6. Okay, so we have designed it such that we wanted certain type of phases to form. Okay, so that's the reason why we have chosen such ratios. Okay, now certain products which are available in the market. So you have here the magnesics, and then you have here from the Biotronic, that is the stent material. Now, their project is called as DREAMS, that is nothing but the drug-eluting absorbable metal scaffold. Okay, so certain drawbacks, that is like I said before, right? So right now it is in the development stage, so it is very expensive. It cannot be afforded by common man. And also the composition, they'll tell you, okay, it is made up of magnesium, zinc, yttrium, etc. But they will not tell you how much of zinc, how much of yttrium, what method they have used, so that you cannot replicate the exact method in your lab. Right? So the composition and the processing techniques are closely guarded secrets. Okay? So, like I said before, I'm going to emphasize more on the overview part, okay, because the concept needs to be understood more clearly rather than the results part. Okay, results will anyway, I'll just go through them, right? So in our project, what we aimed for is to develop new materials to study the electrochemical behavior. We have developed fluoride coatings, and we have performed some biocompatibility studies. So whenever we design a new material, of course, we cut it, we make small samples, we polish it. First thing that you do is microstructure. And in the microstructure, the first thing that you do is X-ray diffraction. Okay? So perform X-ray diffraction, get the information of the different phases that are present. Okay? So we index the peaks, and we get some information with respect to what are the different phases that are present. Then we do the optical, right? So in the optical microscopy, so the etchant that we have used here is acetic picral. Okay, acetic picral is a combination of picric acid, acetic acid. There will be some distilled water and pure ethanol. The recipe is available in the ASTM standard, which works excellent for such alloys. So So for the as DMD microstructure, we have observed a very large grain size. We have seen certain porosities. We could see certain secondary phases that are very large in size. Okay. Whereas once we extrude these materials, what we see here is that the grain size becomes fine grained, right? So you could see here certain black marks here. Now, these are the secondary phases that have got deformed along the extrusion direction. Okay, so you see here the extrusion direction is vertical, here the extrusion direction is horizontal. Okay, and for this particular alloy, we could see some sort of a bimodal distribution. So you have certain coarse grains, certain undeformed grains, and then certain fine grains as well. Okay, we are going to look that in the EBSD. Well, this is the SEM and the EDS images, wherein you get information about different phases, morphology of the secondary phases. Okay, so these are for the as DMD microstructures, and for the as extruded ones, you can see here the secondary phases are nicely elongated along the extrusion direction. Well, we perform EBSD. Why? Because we need to understand the texture and information, and also it will give you a more clear picture about the orientation of the grains with respect to one another, and one can also calculate the grain size very precisely using this technique. Okay, so EBSD stands for electron backscatter diffraction, and you require, like our earlier speaker has mentioned, magnesium is very tricky. Okay, it's not just like how you deal with steels. If one is expert in steels, who has worked for about 10 to 20 years in steels, you come to magnesium, you start dealing with the sample. It's very difficult to polish. Okay, because magnesium is so soft that any additional stress that you introduce, it will give you scratches, and scratches are very bad when it comes to analyzing a microstructure, because you take a scratch sample, go inside a SEM room, perform your experiment, you will not get good result, your slot is waste, you have to go back and prepare your sample. That takes time. Okay, so in all materials, of course, preparation of sample is very important, but like I said before, magnesium is slightly tricky. Okay, well, to get such beautiful images, we had to polish more precisely, go up to, let's say, 1 micron or even 0.5 micron diamond paste, and then we used ion milling so that we remove the top surface layer. If it is again magnesium, after polishing, you take out, in the atmosphere it gets oxidized, right? So we ensure that the sample is always kept under desiccator in a controlled vacuum, of course. And let us say that if I'm going to perform my SEM analysis tomorrow morning, today evening I'm going to load my sample. Yeah, why? Because it will be inside the vacuum, inside the SEM chamber, and tomorrow I just go and start my experiment, right? So it is not just a preparation methodology, it's also got to do with how nicely you treat your samples, right? Well, so pure magnesium, you all know you have basal planes along the to the extreme. Whereas if I add alloying elements, then I will see that there will be small shift in the basal plane. It will be oriented at an angle to the extrusion axis. For the 2 zinc 2 erbium alloy, what we have seen is a prismatic component forming, and the basal texture is disappearing. Okay, you can see here that for this particular alloy, we could see that you have certain DRX, that is a dynamic recrystallized grains, which are fine in size, and then we also have some coarse grains which are not dynamically recrystallized. Yeah, so these are partially or not recrystallized grains. Now they have a very dominant prismatic texture. Okay, and that's the reason why you could see that the overall microstructure exhibits that texture. Right. So here for the other alloy also we see that the textural components are dispersed. Okay, so that what we can see in the end is with hot extrusion for the alloys, if we introduce have the texture the pure magnesium which will be different. Here is one technique by which you can calculate the Young's modulus, that is called as the damping method, the damping loss or the impulse excitation technique. So you take a sample, you place it on the equipment, on some wires, and then you use a tuning fork, and then you introduce certain vibrational frequency into the material, and then because of the excitation you get the vibrational signal from the material which you can plot as a function of time, the amplitude versus time, and then you can calculate the elastic modulus using the damping loss rate. Okay, so using this technique, apart from your typical tensile test, you can calculate a non-destructive method of calculating the Young's modulus. So with this, we could find that the Young's modulus did not change much with the addition of alloying elements, which is good because we do not want too high a Young's modulus. We want it to be in the range of 43 to 45 GPa for the magnesium and its alloys. Tensile properties, well, we have got about 192 megapascal. For pure magnesium, it is about 100 megapascal, the yield strength. Okay, and of course, the ductility values also we have got. We have not compromised on the ductility as well. So, with the increase in the strength, we have also enhanced the ductility. Small examples of the flactography here we have for pure magnesium. It fractures by cleavage mode, and you can see here for the alloys, you could see some dimples forming here. Okay. Compression properties also improved for our alloys. You can see that the ultimate compressive strength is as high as 501 megapascal. We could also see some twins for our samples. Okay, extension twins, that's the tensile twins were formed, and in some studies we also saw that by activating such tensile twins, it can reduce the corrosion rate, okay, of the alpha magnesium matrix, and it will weaken the corrosion anisotropy between the two differently oriented grains. Okay, why? How does it work? Because it works something similar to that of your grain boundaries. Okay, how grain boundaries, they act as physical barriers to the corrosion attack. Similarly, the twin boundaries, they also act as a physical barrier to the corrosion attack. Okay, so they also, the activated twins here, they also increase the protectiveness of the surface films, and it suppresses the microgalvanic or microcorrosion couples, occurring in the twinned grains here. If I want to see the nanoprecipitates and understand their structure, I go for TEM. We can see certain TEM micrographs over here. So for DMD, we could see that there is a huge chunk of the undissolved master alloy. So when we add magnesium, we used magnesium turnings. Okay, zinc we used pellets, calcium also we used pellets, and all the three were used in its pure form. When it comes to erbium and many other rare metals, rare earth materials, now they're very expensive. Okay, they are hardly used in the purest form. Okay, so they are available in what is called as master alloy. So you have an alloy which is already, there will be a major amount of magnesium, 30% of erbium. So when we add this master alloy into my composition, I change my pure magnesium component such that There's already magnesium here in the master alloy. So I designed my addition of different weights of raw materials such that I get my desired final composition. Okay, and as you all know, rare earths are highly available in countries like China, right? So most of the rare earth alloys we get from China. All right, so for the extruded samples, we did some TM analysis. We could see the presence of the W phase, Mg3, zinc 3, erbium 2, very small nano sized phases. And we also did some high resolution imaging to calculate the respacing so that we confirm once again that it is the phase that we're talking about. Okay. Similarly, for other alloys, we also did some calculations. And we saw the presence of what is called as an I phase, that is the icosahedral phase, which if you have studied crystallography, you can say that this particular phase, it exhibits the five-fold rotation symmetry, and it is forbidden symmetry. Okay. Some more discussion. I will not really go through it much. Strengthening mechanisms. Our professor in the our earlier speaker has already explained about different strengthening mechanisms. These are quite basics. You already know that before. Hall patch is for grain refinement. Solid solution, you know what it is. Precipitation strengthening also. For corrosion behavior, we perform the experiments in electrolyte called as phosphate buffer saline. Okay, it's in short PBS. This is the composition. Either you can prepare this in the lab, or from Sigma Aldrich you get PBS tablets. So one tablet in a 200 ml distilled water will give you this composition, right? And we use this electrolyte to perform different corrosion techniques. You know that you can do what is called as immersion test, right? That is a rate loss. So you immerse your sample inside the electrolyte, take it after 1 day, and do the rate loss. So how do you do weight loss? So you take the sample out, there will be some oxide forming on the surface, remove the oxide, and then you have your sample, whose weight is obviously lesser than that of your initial sample. Now, how do you remove the oxide layer? It's not so easy, because if you do that in a mechanical way, there's every chance of removing your actual metal also. Okay, not just the oxide, you may even remove your metal also, right? So we use what is called as chromic acid. So, but be careful if you're using chromic acid, please use a fume hood. Chromic acid is again carcinogenic, and chromic acid makes sure that only the oxide is removed, so that you will get your uncorroded, or the sample which is still the bare sample, right? That's the immersion test. So you do for 1 day, you do it for 3 days, you do it for 7 days, and then you can study the evolution, how the corrosion rate, or rather how much degradation in weight percent takes place. Hydrogen evolution, like I said before, let me show you a particular setup here. You place your sample, you place an inverted flask, you place a test tube on that. Of course, the sample should be inside the corrosion medium. You create a water bath such that the water bath is at the temperature of 37 degrees Celsius. So you perform your test at 37. And what happens here is that as test progresses, inside the flask, there will be some amount of electrolyte, right? So that electrolyte, the level drops after a period of time. Why it happens? Because when the level drops in that particular region, hydrogen will be occupied. Okay, so when magnesium gets corroded, there will be evolution of hydrogen. How much hydrogen is evolved? Now, depending upon the stoichiometry, you can come to a conclusion that this much magnesium has got corroded. Okay, so here you can see for pure magnesium, we could see that there was a rapid dissolution, whereas we had certain controlled degradation for the alloys. We performed in sodium chloride and also in PBS. There is another technique here, which is the potentiodynamic polarization, which gives you a plot of current versus voltage. Again, here you can get an idea about the corrosion potential. And using the values of corrosion current, you can calculate the corrosion rate as well. This is a feature of your sample. You can see here the pure magnesium. Just after 1 day in sodium chloride, it looks like this. After 3 days, and after 7 days, you see what happens, right? The structural integrity is lost. Whereas for the alloys, you see here, not so bad, right? It degrades, of course. We want degradation, right? It's not like we want completely inert material. We want it, but it shouldn't be as high as that of magnesium. As you can see here with the weight loss, within 1 day, our in the sodium chloride solution, within 1 day, we had about 38% weight loss for pure magnesium. Similarly for PBS, slightly reduced, but you can see here the formation of oxide here, right? All right, then there is another technique here which is called an XPS, that is to study the surface layer. So because of these studies, we could see that the erbium element that we have used, it is found in the surface of the corroded sample. Okay, and we could see that the Mg2 plus cations were replaced by the erbium, and this is a higher atomic number element, and the presence of this, so you will have a larger erbium atom that replaces smaller magnesium cation, and that will suppress the penetration of further chlorine anions coming into the contact with the film. Okay, so this is a mechanism behind enhancing the corrosion resistance because of the presence of the rare earth. Okay, can you see my screen?
Yes, sir. It's
okay,
visible.
Yeah, so if your grain size is finer, then you will have, like I said before, there will be more barriers for the corrosion to take place, and we could see that extrusion gave you a better corrosion resistance than the as DM samples. Now the oxide layer here, it may start developing cracks because of the compression stress between the matrix, and this can arise because you have two different crystal structures. MgO will have a different crystal structure, magnesium will have a different crystal structure, right? But if you have more number of grain boundaries, now that could help in compensating this mismatch in the two crystal structures, and it can reduce the compressive stress. Okay. Also, when we discuss about what we call the galvanic effect, so galvanic effect, as you all know, if you have difference in the potential, corrosion potential of electrochemical potential of the two elements, you have the galvanic corrosion that take place. So our secondary phases were more stabler than that of the pure magnesium. But if they are uniformly distributed and if they are fine in size, then we can have what is called as the barrier effect. That is nothing but the corrosion will stop developing from grain to grain. Okay. All right, we did some coatings. These are certain results for coating. So these are the coated samples. So we could see some hydrophilic coatings. That's the fluoride coatings, which improves the cell adhesion and proliferation. These are certain contact angle measurements. So this is a fluoride coating here, what we have done. And you could see here, the fluoride is more or less uniform along the surface, and because of fluoride coating we could see that the red ones are coated ones The black ones are the uncoated ones, and you can see there is a shift in the corrosion potential towards more positive or more nobler values for the coated samples. This is the mechanism of the fluoride coating. So you have in the beginning the evolution of hydrogen, formation of hydroxide, and then when you introduce that into an HF, hydrogen hydrofluoric acid, then you will have the stability of the hydroxide, because in the acidic solution the hydroxide is not stable, and you will then get MgO, MgF2, and then that is the overall reaction. Small overview on the biocompatibility. So this is how we have a protocol, the ISO 10093, I think. That is the standard that we have used. Okay, so first of all, you need to sterilize the samples. Very important. Sterilize it such a way that it doesn't affect the microstructure of the sample. And you take the material and you dip it in the medium to reach some ratio of 3 centimeters square per ml, and then you do the extraction process. Then we use some kind of cells. So these cells are nothing but is derived from the mouse. Why we have done it? Because it can replicate the human bone cells. There are different recipes for this. Okay, so we follow this particular protocol. Then we do the seeding. Then we add a blue alarma solution. Okay, so what we do here is the cell viability test. So cell viability test means in the beginning you will have live cells. You will have a count. Okay, imagine I have about 100 live cells. Now I introduce my alloy. After some period of time, then you count how many live cells are there. Whether this 100 is becoming 90, 80, 0, or 110. Yeah, there is all this possibility of the cells. It could increase in its number as well, which is very good. Okay, so the ISO 10993 tells us that if we have anything and above 70%, which is acceptable. So among all the samples, we could find acceptable values, certainly high for few alloys. And you see this is the pure magnesium, whereas all others are fairly good. Now these are the coated samples, fluoride coated samples. So this is 12-hour dip coating. So if we go for 24-hour dip coating, you can see increase in the viability. Okay, few conclusions here. And before concluding, I would like to share a few interesting reading, which I always encourage the audience every time. Related to my topic here, there is a few interesting reading here. The first one is herion.de, right? So we have, can you see the screen?
Yes, sir.
No, the website I opened.
Yes,
now.
sir. Yes, sir. Yes, sir. It's
Okay.
around. Yes.
Yeah. So if you go to this, what is this? This is Helmholtz Zentrum. Okay, Gstaad. I think it's in Germany, right? So if you go here, you see that they work a lot on such materials. Magnesium-based materials for mostly for biomedical applications. It's certainly very interesting place to visit. Another link here, which I want to show you, is the DREAMS, the project from the Biotronic company, right? So they have now done the second trial. You see here, there is plenty of hiccups, to get the CE mark. CE mark is Conformation European. It's a French term. The CE mark, if it has to fall on a particular implant or a particular biomaterial, it takes a lot of procedures. Okay. And it is again very interesting to see this particular project. Well, so far, it has not really come into the commercial market. Okay. Human trials, it's still in the trial phase, right? So it's still not yet in the commercial market. Third one, what I wanted to show you is that Magnezix. Okay, Magnezix is uh, the screws. Okay, the screws here. So it is designed by a company called as Syntelix. Okay, so this is also quite interesting. You can go through this. You see there are different types of screws here. There will be different descriptions here. It's quite fascinating. If you want to look more into the clinical trials, okay, just like how you have a patent, here you have this website wherein you will see, okay, what is the clinical trial that is going on right now. You can see here the DREAMS project. There are about 123 participants. There will be, of course, it's an interventional, goes inside your body. What are the different outcomes that they see, and so on. So this is also very important. And you see, they will have certain eligibility criteria, right? So only within these people can be subjected to a particular study. That is one thing. And last is this particular paper, dreams of a bioabsorbable stent coming true, right? So we all hope that we will see one fine day wherein our permanent implants will be replaced by such temporary implants made up of magnesium and other materials. And this will be a huge revolution in the medical industry. Okay, I would like to conclude this presentation and the session, and also perhaps the FDP, by thanking the organizers who have given me an opportunity to present my small work. Over to you.
Thank you, sir. It was a very, very pleasant and very informative session. Thank you very much. Dear participants, now the session is open for queries and questions. If you have any queries, please raise hand in Google Form. I will connect you with the speaker. Or if you have any kind of network issues, you can write down in chat box. I would direct it towards speaker. Dr. Pankaj Kumar, you may ask your question now.
Thank you, sir. Myself, Dr. Pankaj Kumar Singh from IIT BHU.
Hello.
Your presentation was nice, sir.
Thank you.
As I see your topic that is concerned with the rare earth, but you are more centralized in ER, that is the erbium. Why you consider that only a rare earth?
Yeah, so we wanted to address a certain gap in the literature, and what we understood was we also did certain work on yttrium as well. That is magnesium tin yttrium. We have done a few studies, but when it comes to erbium, what we observed was, like I said before, playing with the zinc to erbium ratio. So if I have zinc to erbium ratio as 1, then I get the W phase. If I have zinc to erbium ratio of 6, I get the I phase. Okay, so somewhere in between, if I have zinc to erbium ratio, I can control the presence of I phase and W phase. Okay, so our major interest was how to form these phases and what effect these phases will have on the corrosion. Okay, so we could see that such phases are easily formed with the presence of erbium, and that was one reason why we chose erbium, and moreover, it is just to address the gap in the literature.
And another thing I want to share that you have shown the sterilization temperature of 170 degrees centigrade in your slide. Why you have shown that? Actually, this is about 121 degrees centigrade. Why you have considered the 170 degrees centigrade for the sterilization?
Yeah, we wanted to ensure that we finish sterilization within an hour or so, and we did not want to increase time here. So that's the reason why we have increased the temperature.
No, but it is very much serious matter what you are saying, and you are not giving a proper reason behind that. Actually, we also do sterilization process, but that is limited to 121 degrees centigrade. Is there any specific, that is 15 minutes or 30 minutes, I know, that is not new thing. But why you have considered 170 degrees centigrade?
Yes, sir, we have followed a particular protocol, and we go with the protocol. So 170 degrees does not really cause any adverse effect on the sample. We have not, as you can see in the images here, you could see that it did not cause any adverse effects. Barring few samples which have got corroded, that is because this is pure magnesium, whereas for the other samples, it is still intact here. So I think 170 is also fine.
Do you try it at 121?
No.
Okay, thank you.
Thank you.
Yeah, participants, any queries? You can either write it down in the chat box, or you can raise your hand. I can direct it towards your speaker.
Sir, I have a small question.
Please go ahead,
Sir.
Rashmi.
Yes, sir. Actually, whenever we are doing some test, always we go with a mouse or rabbit or dog, that kind of thing whenever we are doing the testing, not directly upon a human body. Why those animals are selected, sir? Can you tell me the reason?
Yeah. So, like I said before, what we've used here is the MC3T3, that is the cells derived from mouse. So
Yes.
the body condition of mouse or rabbits, it's more close to that of human body. Not exactly, of course, but then the fluids inside the rabbits and mouse, the cells, they're quite similar to human body. Okay, so predominantly they are done in rabbits, and well, if you have mouse, then you go for mouse as well. Okay, but predominantly we could see that there is a certain breed of New Zealand rabbits wherein such tests have been done.
Okay. So regarding dogs, sir?
I have not yet come across such studies in my literature, so I'm not very sure about dogs.
Okay, sir. Thanks.
Thank you for your question, Rashmiji. Any participants, any more questions? You can either unmute yourself or raise your hand, or if you have any kind of problems experiencing due to network issues, you can write it on chat box. Okay, sir, I do have a question from Avik D. Is coating material has any influence on biocompatibility? He wants to ask that.
Yeah, so coating has definitely increased the biocompatibility. Like I said, the cell adhesion and cell proliferation increases with respect to coating. But however, we have performed these experiments, the biocompatibility tests, only on the coated samples. Okay, because that was our goal. So we haven't really done biocompatibility tests on the uncoated samples. But the coated samples is definitely exhibiting better biocompatibility results because the cell adhesion is increased because of the coating.
I hope you have Avik D, your question has been answered. Is there any more questions? Participants, you can either connect us through chat box or you can unmute yourself. Now the session is open for Q&A.
One thing more I want to ask, sir.
Oh, go ahead, sir.
In most of the cases, sodium chloride is used in the rusting experiments. Why this is used only for the research purpose?
Well, when it comes to corrosion, right? Like I said before, magnesium has the effect of pitting. So pitting happens predominantly when you have a chloride solution, and sodium chloride, it is not coming in the bio-corrosion aspect, of course. It is coming in the general corrosion aspect. So, which is something readily available, the sodium chloride solution. It's not really the table salt. We purchase standard sodium chloride salt, and then we prepare it, the solution in the lab, right? So, for example, if I perform sodium chloride using sodium chloride, the experiment, right? If I use 3.58%, which is equivalent to that of seawater, the concentration, which is too high for magnesium. Okay, so for magnesium, I use maybe 0.58%. Okay, so the results that I get using sodium chloride, I can compare that with the results performed by somebody else for different alloys. Okay, so it is predominantly used in the scientific world, primarily because number one, it is easily available. Yeah. Number two, because, for example, I come from a city called Mangalore. Mangalore is in the coastal region. Now, we have a lot of corrosion taking place in the railings and in the buildings and so on. So we are actually in a corrosive environment, the coastal cities. Now, how does it happen? Why coastal cities are affected with this? Because you have the chlorine or the seawater, the chloride ions that are affecting. So this is one of the reasons why we predominantly use sodium chloride solution. But definitely for biocorrosion, we do not use.
Is there any substitute on the place of sodium chloride?
Yeah, well, we can also use sodium sulfate solution as well.
Thank you, sir.
Thank you.
Dear participants, if there are no more questions, if there is any, then please go ahead. The session is open for queries. So if there are no more questions, then we would wind up this session. Thank you, Dr. Devadas Bhatt, from the whole FDP organizing team, as well as our college, JNNC Shimoga. We thank you for beautiful presentation and knowledge sharing about in this session. And also, I think many of the researchers might have discovered a new way of going into about this research, which is not only because of your finding in magnesium alloys, it is also about the experimentation and the methodology which you have used and have told us about. So we are very happy about that, and from the whole team, I humbly thank you, sir. And we'll be starting our validatory function around from 3. Please, I ask your humble self to be on 3, and all the questions about the quiz and the feedback form would be shared in that program. Okay. Thank you very much, and I thank you, sir. Over to you.
Thank you.
Okay.
So means that the program will start at 3 o'clock, not 2.
Not 2, 3 o'clock.
Okay, okay. That's the revised time. Okay.
Yes, for validatory, we will start from 3.
Okay.
Okay.
Hello, sir. Hello.
Yes, ma'am.
Is there a test after validatory function?
Yes, ma'am. There would be a quiz after validatory function, and we'll be sharing the link in the ATAL FDP WhatsApp group. So the link and everything about the details would be shared in that function itself, because if I have seen that many of the participants has already left, so if I share that information, many of you might not get it. So on the validatory function, please be present. I will be sharing a link in the WhatsApp group for the quiz.
Thank you, sir.
Okay. Yes, Mr. Harish Garg. Mr. Harish Garg. Mr. Harish Garg, if you have any query, please. Okay, so we'll wind up this session and we'll be meeting around 3 for sharp 3 for valedictory function. I again ask your humble self to be present on time. Thank you very much, and we'll see you soon.